and to the people who are following us online. So we are very glad to be back in person, or at least in this hybrid version, for this year's Cardiff analysis seminar. So we are delighted to have Alex Sobolev from UCL today. We'll talk about spectral properties of the one particle density matrix. So Alex, take it away.
Thank you very much. Oh, it is so nice to see live people in the room, I must say. And I also thank those who are there on the other end of the camera for coming to the talk. And I hope you will hear me. I will try to speak as clearly as I can. So, spectral properties of the one particle density matrix. Okay. Yeah, right. So, what are we talking about? We are going to do mathematical quantum mechanics. Mathematical quantum mechanics. So I will start with the Schrödinger operator that describes n particles in the field of a nucleus. And these are Coulomb particles, all of them. And the attraction to the nucleus is also Coulomb type, as you can see. So if we have n particles, we can think of them as electrons. I will come back to this point a bit later. Then we have, for each particle, we have a kinetic energy operator, which is Laplacian with the minus sign in front. And we have a potential that describes interaction of particles. This is the interaction term. This is the repulsion. Electron-electron repulsion comes with the plus sign, and the attraction of the nucleus comes with the minus sign, of course, and Z is the charge of the nucleus. Now, a little bit about the notation. So here you have x1, x2, xn. These are coordinates of the particles. They are all three-dimensional. So when you put them together, you get 3n-dimensional Euclidean space. The variable bold face x is exactly the collection of all the particle coordinates. And then the important notation that I would like to introduce is that it will be convenient for me to take the whole collection of particles, n of them, and cut off the very last one. And it will be x hat, only n minus 1 particles. So that the whole set of coordinates can be written like that. So it is x hat, comma x. So the last particle will play a special role, as you will see later. So what do we do? Oops. Right, I will show everything straight away. So, as I said, Z is a nuclear charge, and the underlying space, of course, is L2 on 3n. And this operator is, it's very easy to check that it is actually self-adjoint operator on the Sobolev space of twice differentiable in the sense of distributions functions on the whole space R3n. This is a simple exercise, but I found that I have to say it every time when I'm introducing all these objects. Well, I will be interested in eigenfunctions of this operator. Actually, I just need one. And I will pick an eigenfunction. I will denote it by psi. So the eigenvalue, or quantum mechanically speaking, the energy of this eigenfunction will be E. And from this eigenfunction, I'm going to build the object that will be the main object of the talk. Okay, I will show again a few things at the same time. So this is how I will define the protagonist of all this work. So this is our one particle density matrix. Look how it is defined. We split off one coordinate, right? This x hat, comma x. We have two copies of the eigenfunction. In one of them, it will be variable x, and the other it will be variable y. And then I average over x hat. So 3n minus three-dimensional integral here. And the remaining object will obviously depend on two three-dimensional variables. So it is a function of two variables, and which is called the one particle density matrix. And well, you can see here, let me just explain what this means. So in fact, this is a simplified definition. The one that I'm going to work with is a simplified definition of the density matrix. In fact, one has to use, if one wants really to get a more general result, then one has to use the precise definition of this object. And I gave it here for three particle case. And you can guess how it is defined for arbitrary many particles. So here, you see, the first term is exactly the same as there. You just cut off the last variable and you leave it alone and integrate in the rest, t and z. And then the second term, you take out the middle variable, x and y. You see there in the middle, and you integrate over the remaining variables. And the last term, it is the last possible situation. You integrate in the second and the third variable. So that is the proper, most general definition of the density, one particle density matrix. I thought I would show it to you so that you will know that this is not exactly the most genuine object that I'm studying, but for the sake of this presentation, I will just look at this function. So it is much easier, and it allows me to avoid various technical things along the way. Okay, so what are we going to do with that? So
the results also apply to more general.
yes, the result that I'm proud to present applies to more general one. But instead of scalar operators, one will have to consider vector values operators with vector value functions. Otherwise, it is very similar. So what I'm going to do now, I'm going to study the integral operator, which I denote gamma, with this kernel. So gamma xy will be considered as a kernel. So this is going to be an integral kernel. And I will be interested in spectral properties of this operator. I will say a few words about that a bit later, why I'm interested in spectral properties. But let me just give you a very quick and simple calculation that tells us something about the spectrum of this operator, about the properties of this operator. So first of all, look at the definition. We immediately see that because of that integral, so we have actually a product of two integral operators. In fact, it will be just one operator and the adjoint to it. And this one operator will be operator with the kernel psi x hat x. So this will be operated from L2 on R3, as it is written here, into L2 on a much more dimensional space, 3 and minus 3, if we have many particles. So here is the explicit definition of this operator. Now, this is an eigenfunction, so it is L2 function. And when you have a kernel that belongs to L2, this means that the operator is Hilbert-Schmidt. Now, if you have the product of two Hilbert-Schmidt operators, you get a trace plus operator. So already for free, we got this information that gamma is actually trace class, and we actually know the trace or the trace norm, because this is a positive operator. And therefore, the trace norm, or the trace, the point side, is equal to the norm psi squared, which is very nice. But this is not a precise information. One needs to know. Well, let's see what is written here. Right. One needs to know how fast the eigenvalues of this operator decay. So for trace plus, we can say something, they decay in a certain way, but we need precise information about the decay. And what is the reason for that? Why do we need it? Well, of course, when I looked at this problem, it was fascinating and it was funny and interesting for me to solve this problem just as a mathematician. And then when you talk to people in mathematical physicists or people in quantum chemistry, then they will say that this information is actually very important for a very simple reason, that in quantum chemistry, you do calculations by approximating this matrix or this operator by finite dimensional operators, finite rank operators. And it is always a question, how precise is this approximation? And if you know how fast the eigenvalues decay, you will know how precise. So if they decay slowly, then you will have to take a lot of the operator of high dimension to approximate one particle density matrix. I think it will be
But occur.
Yeah, I can hear you better.
All right.
so. The first result, as far as I understand, mathematical result was obtained by Gero Frieseke in 2003, when he was still in this country. And he established that gamma has an infinite rank. So, which is not surprising by itself, but at least this is a piece of information that makes it all make sense. Then in 2020, this is a chemist from Poland. I'm not sure I'm pronouncing his name right, Czesłowski. I think this is the correct pronunciation. He obtained the following formula for the two-particle case. The formula, it was a heuristic argument that indicated that the eigenvalues should decay like this, k minus 8/3. The eigenvalues of this operator gamma. It was done for two particles, and it was not a precise, as I said, it was heuristic calculation. So my objective here is to obtain the formula, the precise asymptotic formula for eigenvalues, and you will see that this formula confirms this heuristic formula. It will be k minus 8/3.
Okay, so
This is what I say. My objective is spectral asymptotics for gamma.
let's go to the next slide. Right.
Right. So here's the main theorem now. Suppose that the eigenfunction satisfies this exponential bound. So the eigenfunction is exponentially decaying at infinity. Is it a restrictive assumption? This is an important question. I can assume anything, and then you will ask me, why do I assume that? Maybe there are eigenfunctions that do not have this property. And it turns out that all eigenfunctions, sensible eigenfunctions, do indeed possess this property. For example, if you take an eigenvalue E, the eigenvalue associated with this function psi, under the bottom of the essential spectrum, then it is a rigorous mathematical result that the eigenfunction does decay exponentially. But this exponential decay is also applicable when you study embedded eigenvalues, as long as they're away from so-called thresholds on the spectrum. Then you also have exponential decay. And I gave here a few names of people who wrote quite a few papers on that subject. So that was first of Agmon. This is a very famous work by Agmon on exponential decay. And also Fröse and Herbst, they did eigenvalues on the embedded eigenvalues on the spectrum. And here's the theorem. It looks very short and nice. So eigenvalues indeed satisfy this asymptotic formula. with the constant A, which is computed explicitly, but for the constant A, I will need a bit more information. So I'm not going to give this formula now. I will introduce it a bit later.
You have this constant explicit. These are the cases in which it is implicit.
Yes, and I will discuss that.
Okay.
Yes. It is, well, you notice this greater oracle. Yes. Yeah, thank you.
Okay.
Okay, so the first step, a sort of simplification, right? You remember that gamma was a product of these two operators, psi star and psi. Right? So this means that eigenvalues of the operator gamma are actually S values of the operator psi. Sorry, singular values of the operator psi. Okay. Right, and then because of that, we can rewrite this formula like this. So nothing happened. I have just rewritten this formula for the operator psi and nothing else. But this makes it conceptually simpler because now you don't have to think about this integral that you average over x hat. You can work with the kernel psi itself, with the function essentially itself. Now, the question is, how fast do the singular values, sk psi, decay, as k tends to infinity? And this is well known that the decay of singular values or eigenvalues, depending on the context, depends very much on the smoothness of the kernel. So for integral operator, the smoother the kernel is, the faster eigenvalues decay. So, and therefore, this dictates immediately that we should study smoothness properties of the function psi. We'll see where it has singularities and what these singularities are and how they determine the decay of the eigenvalues, or more precisely singular values. And on the basis of the smoothness properties, we are going to study, as I just said, estimates and asymptotics of S values. Just read it off the singularities of the function psi. That's the idea. Okay, well, I'll show you two straight away. Okay, so let's discuss the smoothness of the eigenfunctions first. That was the potential, if you remember, in the Schrödinger operator. So it has, as you can see, singularities at 0 and at the coalescence points. So where particles meet, this is where there are singularities. And using the fact that all these potentials are Coulomb potentials, Coulomb potential is a real analytic function in three-dimensional, at least in three-dimensional space. So by the elliptic theory, the eigenfunction is also real analytic away from singularities. So where you have smooth Coulomb potential, you have real analyticity of the function psi. This is one can say, standard result. Good to know that, but what happens at the singularities? At the singularities, you have Lipschitz behavior. This is what Kato proved in '57. This is a seminal work which is cited, which is quoted essentially everywhere, not only by mathematicians, but also by physicists and chemists. This is one of the main references. That was quite surprising for me when I found this out. When I asked this Czeslovsky, I asked him, where is this information can be found, the one that he mentioned to me in one of his emails, and he said, I will send you a link. And he sent me a link to Carter's paper, which I already have, of course. So what is next? So here, these are names of people. So this is Fournet, Thomas and Maria Hoffman-Ostenhoff, and Thomas Sorensen. They studied in a series of papers, they studied detailed behavior of the function psi in the vicinity of singularities. Well, it is good to know that it is Lipschitz, but one needs to know a bit more in the vicinity of singularities. What kind of Lipschitz function is it? What does it look like? And is it always Lipschitz? Maybe it is beta sometimes. So here is the result. So I'm going to give you the result, which is actually the most important one for the asymptotics. And this is a consequence of, it follows from one of the papers of those authors that I just mentioned. And I will show it here just in a few seconds. So look at this. Let me just define this set. This is the set Uj. This is the set in R3n. So this is the big Euclidean space that is a configuration space for all the particles. So this is the precise definition, but in words, let me just describe it in words. So this is the set where none of the particles touch. They do not hit the nucleus. They do not hit each other. All of them, none of them touch except for one pair of particles. And this is the pair X, as you can see, the J is missing from here. So X can be equal to Xj. So this is the point, this is the situation when you can actually put two particles together, assuming that everything else, every other pair is separated. So I wanted to draw a little picture. I might need it later. So this is the nucleus. You have X1, X2. Well, assume that we have three particles, so it is going to be this is the bold X here. And then imagine that X1, X2 are fixed. They do not touch each other. They do not touch the origin where the nucleus is located. And you have the third particle that wanders around. So the set U2, for example, would allow these two particles, X and X2, to come very close to each other and actually coalesce. But X1 is always separated from those two. Okay. U1 would be the set where the particle X can touch X1, but we separate it from X2. That's the idea. And this is the set in the space of dimension -3, so 3 and -3, where X indeed coincides with Xj. So this is when they hit each other and they just merge. Right, so I call it UJD, diagonal. And for this set, we can say the following. So imagine, so you have this UJ, you fix it, right? So for each of these J's, one can find a set, omega J. I need to draw another picture. But let me just state the theorem and then I will explain. There exists a set, omega J, this is an open connected set, which contains the diagonal, but it is contained itself in the bigger set Uj. And on this set, we can describe the eigenfunction in the following way. So that is the representation for the eigenfunction on this set. What is important that two particles are allowed to touch each other. and only two particles. Right? The other particles are separated. So there are two functions that I denote by psi j and eta j. They're both real analytic on omega j. I will show it in the picture just in a moment. And the function psi is represented as this sum. So this is the real analytic term. And then there is also real analytic factor eta j, but there is this explicit Lipschitz factor, xj minus x. So this is where a Lipschitz property comes in. And this is exactly what is very useful because you have an explicit Lipschitz factor here. This is probably the simplest, the most elementary example of the Lipschitz function. And this is actually a remarkable result because the rest of this in this formula, the rest of this formula, these are analytic functions. There is only one Lipschitz factor, very explicit one, and the rest is real analytic. Which is, you want to say something?
I want to ask if I understand correctly, that means that you precisely understand the Lipschitz singularity.
Yes,
Of
this is the precise description.
Often you know precisely how it's right.
Exactly, exactly, yeah. So to show this on a, now I'm going to draw a different picture. Here I had two-dimensional particles, right? They were frozen and X was wandering around. And here, let me just look at two particles, X and X1. And then, so this is the origin. The set Uj will be, this is U1, set U1 will be this. So first of all, none of these particles touches the origin, so we throw from this plane both axes, and then the diagonal will be this. This is where they meet. This diagonal is, of course, included in the set Uj, right? U1, the set U1, but the origin is out, the origin excluded. Now, this set omega is going to look like this. So it is something that includes the diagonal, it is contained in U1, right? But it doesn't in general coincide with U1. Okay. Well, okay, so that's the representation. Why is this representation that actually determines everything? Let me explain this. Here is the theorem, which I call proposition, by Birman and Solomyak, established in the 70s. I put the date there in 1977. It was just one of the papers, but this is the result that can be found in various papers. And this theorem explains why this specific form of the singularity, the Lipschitz singularity, in our case, why is this specific form of singularity actually allows you to find the spectral asymptotics. So that will be the important result for us, important proposition. So we have, let's take two sets. Think about X and Y as two cubes. It doesn't matter. I wrote it for arbitrary parallel sets, but bounded parallel sets. Let's think about two cubes, X and Y. Actually, we can think about the same cube. So operator acts from the cube, L2 on the cube, into L2 on the same cube. Notice that X and Y have the same dimension. Okay, they have the same dimension. So you remember that function psi, it has the variable that is 3n minus 3 dimensional, and this one is 3 dimensional. So this cannot be applied to function psi explicitly, immediately, but let's just get on with this proposition first. Then I take an operator with this kernel. This kernel, so look at this kernel. It contains two weights, row 1, row 2. They're just bounded weights. They're assumed to be bounded on the cubes. Cube. then it has this function of two variables, which is smooth, and it is smooth on the closed cubes. So you can control its behavior all the way to the edges, to the faces of the cube. And I left it for the last. So this is the factor that determines everything. This is x minus y. This is the homogeneous factor, homogeneous kernel, right? Homogeneity alpha. And notice that this kernel depends, this homogeneous factor depends on the difference. This is also very important. So you can take, so you can describe this operator doing Fourier transform. You can describe it as a multiplication operator after Fourier transform. And the homogeneity should be not too negative. So greater than minus dimension. This would ensure that the operator is bounded and actually compact. And then under all these conditions that I just wrote down here, this operator is compact and its singular values satisfy this formula. This is the asymptotic formula for singular values. Look at this exponent p. So the eigenvalues of, singular values, decay like p minus 1 over p. 1 over p is given by this formula. So if you have very large alpha homogeneity of the kernel, then you will have a very quickly decaying set of singular values. Okay, so the dimension also enters this formula. So if alpha is positive, so this is going to be greater than 1. If alpha is negative, it goes to minus d, then p minus 1 becomes very, very small. So you this goes in, this is in line with the observation that I pointed out previously, that if you have a smooth kernel, the singular values will decay fast. So if the homogeneity is higher, it is smoother, it is differentiable more, therefore the eigenvalues will decay faster. So this is the explicit formula. As you can see, the behavior of this function phi on the diagonal is important. And only that, nothing else. You don't need to know the details of this function outside the diagonal for this formula. That's the important part. And, well, coefficient is given explicitly. Notice that if you take even numbers here, even positive or non-negative numbers for alpha, then you will get a C-infinity kernel, and the eigenvalues will decay infinitely fast, which, of course, is reflected in this formula, that the coefficient is 0. Eigenvalues decay very fast. So it has to be non-smooth for this formula. And then you will have this power-like decay of eigenvalues of that type. Okay. I understand that I'm going a bit slow. If you think that I'm going a bit slow, I can. Is it okay? I will not be able to tell you all the details. Actually, I wasn't going to. I just want you. I want everybody to understand what's going on. Okay, so that's the basis. That's the basis for our calculations. This formula.
Let's go to the next slide.
Not next slide. There is something else here. Yes, indeed. So you remember that formula that I wrote before. So this side is this. Remember this formula. So this is the singularity, which is Lifshitz. So homogeneity is 1, right? Homogeneity is 1. Dimension is 3, right? If you look at 3-dimensional particles, of course, and therefore 1 over p is exactly 4/3, and we have the formula that I promised you from the start. So in this formula, A will be calculated by this formula.
Okay, so it will be exactly as what we expect. Okay. Now, on this slide, I will just show you the formula for the coefficient A. There is one thing that I haven't mentioned before, but I will have to mention it here. So let's take two-particle case, just for simplicity. Notice that in the previous proposition, I pointed this out, that both cubes are of the same dimension. Actually, it is the same cube. But once you look at this function, then these variables, they have different dimensions. So that proposition is not applicable directly. One has to play with it somehow. But for two particles, it can be applied because both variables have the same dimension, right? X1 and X2, or X1 and X. So let's take two particles for this reason. Then you have this formula for the function psi. Then let me forget about this term for a while. This is the smooth term. It is real analytic, and therefore the eigenvalues will decay very, very fast. So we don't care about it. We care only about this term. Now, can we apply that proposition straight away? And the answer is no, because that you remember the proposition about the structure of this function, about the structure, doesn't tell you anything about these functions on the closure of the set omega. You remember there was set omega here. And in the proposition about eigenvalues, or about the decay of eigenvalues, we needed the function, the coefficients that are smooth all the way to the boundary on the closure. The structure proposition, the structure theorem didn't give us any information about that. So this is why I have to include this part in the main result. So that in spite of the fact that we don't have this information from the theorem that we are using, but the structure theorem, then we still have this nice property. If we take this function eta on the diagonal, so xx, then this object, this function will belong to this funny L space, L3/4, so it is less than 1. So, and this integral will give you exactly the coefficient A. But the fact that it belongs to L3/4, it needs to be checked. It needs to prove. It needs a proof. It is not clear from the start. So this is two-particle case. Let me show you quickly three-particle case. So if you have three particles, therefore you have two functions eta, right? When third particle coalesce with the first, or third particle coalesce with the second particle. So you have two functions eta. And then look what is happening here. So we don't make a statement like this straight away. We look first at these functions, eta1 and eta2. And they are built in a very similar way. But we take two particles. This is the first and the last on the diagonal. They coincide. And this gives us a function of the middle variable. Then we take the function eta2 that describes the interaction of second and the third particle. So we take them on the diagonal. So this is where they coincide. And it will depend on the first variable, three-dimensional variable. So both these functions, as functions of this middle and the first variable, they turn out to be L2 functions on R3. This is also a theorem that needs to be proved. For almost all x in three dimensions. So for these variables. And now this new function h, as you can see, it is built out of L2 norms on those functions. This function now belongs to L3/4. So again, the same story. It needs to be L3/4. And then coefficient A is given by a similar formula, but the expression for this function is more complicated than here. And if you have many particles, then it is more or less clear what you need to do. You fix the pair, and then the function will be L2 function of the remaining variables. Then you integrate in those remaining variables, and the result will belong to L3/4. And again, the result is like that. So that's the formula. And well, I'm not going to go back to the previous, maybe 2 previous slides, but this formula follows from Birman-Solomyak formula. This is exactly what they wrote. 3/4 is exactly one of it is P. This is the parameter P, 3/4. Okay. Now, the question is, can A be equal to 0? Yes. And here's the reason. This is actually, at the same time, this is very simple, but I for some reason, when I wrote this first version of the text and I put it on archive, I had again a comment from the chemist, from Czeslovsky, and he said, why don't you discuss why the coefficient A could be actually 0? And so here is the result of my discussions with him that I'm going to report. Now, when mathematical physicists, with the emphasis on mathematics, they give a talk about quantum mechanics or structure of molecules or atoms, they always think about electrons, of course, as fermions. And for simplicity, it is very often assumed that these fermions are spinless. So there is only spatial variable, no spin. And to say that the particles are fermions means to say that the eigenfunction or wave function is antisymmetric. So actually, it will show up, but I will write this anyway. For two particles, this is just that. Antisymmetric with respect to permutations. However, if you include the spin, so you attach another set of variables, spin variables, right? So now antisymmetry can manifest itself in a few different ways. So let me show you what I mean. So the first, let's take two particles for simplicity. And then particles are fermions, we assume that. They have spin, up or down. So there are 3 possible configurations that we can analyze. The first configuration, which is called singlet coalescence, when the particles, when the antisymmetry is carried by the spin part, by the spin variables, whereas the spatial variables, the function remains symmetric with respect to permutations of spatial variables. So we're still talking about electrons, but antisymmetry is stored into the spin part. So they have opposite spins. Okay. So this means, so the important conclusion is that the spatial part is symmetric, and then indeed the function eta1, which enters the coefficient, is non-zero. I do not have a proof that this is a non-zero function, but this is what chemists always assume, that for the singlet coalescence, this function on top, as they call it, on top wave function is non-zero. So in this case, A is not 0. Now, the second case is what is called triplet coalescence. So in this case, the antisymmetry is indeed carried by the spatial part. So when you swap the variables, you get minus here. And as a consequence, the function eta on the diagonal will be also 0. So on top wave function will be 0 again on the diagonal. And of course, the coefficient is 0. So this is the case when coefficient disappears. And there is also another case, which is which has a funny long name, this unnatural parity singlet coalescence. So here again, the function is symmetric. So this is singlet, so it's going to be symmetric spatially. Antisymmetry is carried by the spin part, spin variables. And in this case, the diagonal is always 0. So this is what means by unnatural parity. On top eigenfunction is 0 on the diagonal, therefore the coefficient is 0 again. It looks to me that chemists actually do not consider any other types of coalescence, although mathematically speaking, if you consider behavior of the wave function near the diagonal, just take the Taylor series and say, if the first term of the series is not 0, we have that. If the first term is 0, the second is not, we have that. If both of them are zeros, and the third one, I think, is 0 for this result, then we have that, and so on. So you can actually produce lots of types of coalescences, and every time you will get a different type of singularity. But this is just to say that these things can happen, and of course, a natural question is, what will happen if we have, for example, triplet coalescence? And my working conjecture, which is actually the result already, is that in this case, the eigenvalues decay, or singular values of the function of the operator psi decay like -5/3. So it is faster. They will decay faster. The question again, why do they decay faster? Because the singularity here, you see on the diagonal, the singularity will be weaker. It will be of, if you expand this in the Taylor series,
You can see
the second one. The single one?
No, single one, not the PSP.
Yes, thanks. Yeah, this should be SK. Yeah. Sorry about that. The singularity will be weaker for triplets because the diagonal this function is 0, so we have to take the next term in the Taylor expansion, so it will be homogeneity 2. But this will be non-smooth term times smooth term, and that will give us faster decay of eigenvalues or singular values. So I wanted to discuss that, and I'm glad that I did. How much time do I have?
2 minutes.
Okay, so I will show the whole slide then, and whatever I can say, I will. Now, what I wanted to do here, that as I said, the basis for the whole analysis is the result by Birman-Solomyak about power-like decay of singular values of integral operators. But the theoretical tools are on this page. So this is the page about compact operators with power-like decay of singular values. This is a very useful set of notations, first of all, and then there are two results here that play really a pivotal role in the proof. Let me just go quickly through that. First of all, we define a class. This is the weak Schatten von Neumann class. This is why it is denoted P over infinity. This is the class of compact operators whose singular values decay like this. Not necessarily asymptotics, but they have a bound of this order. And then I will introduce two functionals here, capital G and lowercase g. If they coincide, then we have the asymptotics. But otherwise, they're just finite and they may be different. And so asymptotics is here. And of course, when you do asymptotic analysis, what you usually look at, I mean, this is a very standard thing I'm going to say. So you have an operator. You have an operator whose spectral asymptotics you know well, and you have a perturbation. What can you say about the perturbed operator? Is it going to have the same asymptotics, or how is it going to change anyway? So these are two propositions that help to answer this question. So if the perturbation decays, the eigenvalues or singular values of the perturbation decay faster, so this functional is zero, then the asymptotics is preserved. So the perturbed operator will have exactly the same asymptotics as the first operator. So this is something that is useful to know. I'm not going to talk about this today, obviously, but I hope that this could be useful for something else, not only this problem. But second proposition is even more useful, actually, because this is exactly that one that is used most in the proof. Well, for me, it is more useful, but let me just explain what is it. So look at this perturbation multiplied by epsilon. Epsilon, yes. Now assume that this operator, we know it's asymptotics. And we know that operator K also has singular values decaying at the same rate, not faster, like in the first proposition, but at the same rate. But it is multiplied by epsilon. And so what this proposition says is that if this perturbation, if this functional here tends to zero when epsilon tends to zero, then you can find the asymptotics of the perturbed operator just by taking the limit of this functional for the it may be confusing. Yes, taking the limit of the sum of this perturbed operator. You can find the asymptotics of t by taking the limit of asymptotics of operator t epsilon. Okay, so and this limit exists. This is also part of the statement. The limit exists, and it gives you exactly the functional GP and lowercase g as well. Okay, so when you have perturbation multiplied by epsilon, this is a very useful result that allows us to take epsilon to zero and to take to get the asymptotics. Okay, I guess I have to stop now. Yes, I do. Probably. Yeah. So I stop. Thank you very much. Very few.
We will now take questions from live attendees and virtual attendees. But before that, let me give an announcement for next week before I forget. So Cardiff University is changing the convention about the scheduling of lectures. So we will change the scheduling of seminars as well. So we will no longer start at 2:10, but we will start at 2 sharp from next week. So both the live seminars and in-person seminars will start at 2 sharp, and we carry on until 3. All right, so any questions from the live audience or from the virtual audience?
So Alex, this last result showing where you have the p epsilons, is this what you use to deal with the fact that you only have results that don't go up to the boundary with the eigenfunction?
Exactly. You cut it down so that you have a nice function, but then you have to take epsilon to 0. And the estimates that I didn't show, they are on the next slide. They actually indicate that it has this kind of structure, the perturbation. So when epsilon tends to 0, it just vanishes. It has the same rate of decay, the perturbation, but it vanishes when epsilon tends to 0.
So somehow it's easier to prove that the limit as epsilon tends to 0 of GP of t epsilon minus t is 0 than to work directly with GP of t.
You mean this? Yes, exactly. Yes, yes. This is.
It's not obvious a priori, but that's an easy hypothesis to check.
This is, yes, so this is something that is really very important, and this is what helps. Then when you have the perturbation, well, in very simple terms, if you have a complicated operator to study, then you can approximate it by something simple looking. But the price to pay is that you have this error that you made, and what can you say about the error? The eigenvalues of the singular values of the error will decay at the same rate, but if you take a better approximation, smaller epsilon, right? This is the approximation. This is the operator that you want to study. So if you take a better approximation, the limit that the perturbation will tend to zero. The contribution of the perturbation will tend to zero, and therefore you can use this formula.
Further questions? Perhaps I can stop sharing so we see our attendees make somebody ask questions. So if not, I will ask a question.
Yeah, go on.
So the heuristic argument we're mentioning in the beginning to see that the power is 8/3. Can you give us a feeling for that argument, or is there an easy, somehow, an intuitive way to see that 8/3 should be the right thing? Or
this is not a very difficult argument, but I was prepared to discuss where the 8/3 come looking at this, where the 8/3 come from looking at this formula. But I haven't prepared the presentation of that result. It is not a difficult result. One can conduct the,
because if you do it from here, you have first to get the result about the structure of the singularity and then use it to guess the 8/3, right?
well, to guess it, to read it off, so to say,
Yeah.
because it will be clear that it will be 4/3 or 8/3. Yes, in this in Chilkovsky's paper, he looks at the electrons and he counts the occupation numbers. This is what he does. So he uses the precise formula for the eigenfunction in terms of Gegenbauer polynomials and
so it's not a spectral theoretic argument.
it is not. This is an explicit calculation, and it doesn't lead exactly to this formula, but he counts a quantity which is very similar to the eigenvalues. And the formula is different. There is a coefficient as well, but it is not that 3/4. It is something else. I don't remember what, another power. I mean, in the coefficient, the power in the integral, the decay is still the same, 8/3, but the power in the integral is different.
Further questions? Not from people attending. So let's thank the speaker again for the very nice talk.
Thank you.
So Jonathan, you can perhaps stop the recording now. Thanks very much.